Hello everyone, welcome to the course Data Structures. This is N. Thulasi Chitra, Associate Professor, Department of CSIT, MLR Institute of Technology. In today's session, we will be discussing about B-Tree-Deletion. Let us see the overview of today's session. Here we will be discussing about B-Tree search first, then we will be looking into B-Tree-Deletion also. With the examples, we are going to see about the deletion part. As you have already discussed B-Tree insertion, if you can refer to that previous video, so that you could understand this deletion part very easily. Let us see searching. First, look into the B-Tree search, how we are going to perform. It will be similarly like the search operation, where we are going to do it in a binary search tree. In the binary search tree, how we are going to perform the searching? As you know that we are going to have the root node on the left subtree. You are going to have all the lesser elements of the root, and on the right hand side all the elements are greater than the root node. And if you have given some element, if the key element is lesser than the root node, then we are going to search on the left subtree, and otherwise we are going to search on the right subtree. Or otherwise, if the key value and root value both are same, then the key element is going to will be found at the root node. So the key element we are going to display it as the element is found in the list. The same process here we are going to apply in B-Tree also. In binary search tree, the search process starts from the root node, and we make two-way decision every time, as we go to the either to the left subtree or right subtree, as I have given you the example. In B-Tree also, the search process starts from the root node, but here we make n-way decision every time. That means here again we are going to have the subtrees, so that is called the n-way decision every time, where n is the total number of children that the node consists of. From that we are going to search for the particular node that is present, or whether it is present on the left subtree or right subtree. And because of this B-Tree, the search operation performed will be big O of log n time complexity it is going to take. This will be the same for the binary search tree also. Okay, and this is very simple if you know about the binary search tree searching operation. Now coming to the next one, binary, that is B-Tree-Deletion. When we are going to do this B-Tree-Deletion, here we come across so many cases, right? What are the different cases that will occur when I want to perform deletion? As we have seen in the BST also, we come across three cases when we are performing the deletion of a particular node. What are the three cases we have seen? We are going to delete a leaf node, or we can say it as a node with no children. And the second one, we are going to delete a node with one children, and the other case, a node with two children also we have seen, right? In BST itself we have three cases, but in B-Tree we have some more cases we are looking into. What are the cases? The first case, observe, if the target key is a leaf node. With example we will see later. First, what are the cases? First we'll look into here, then we'll see with an example all the cases, right? If the target key is a leaf node, suppose in your B-Tree, if the target key is in the leaf node, right? In the leaf node, in that case we are going to check for the first condition, that is, leaf node contains more than minimum number of keys or not. If I have minimum number of keys, then I can able to delete it, right? We need to follow based on this. B-Tree will be followed based on the order of the tree. That is, M represents the order, right? Based on this M, we need to decide what is the maximum number of keys, minimum number of keys that should present in a B-Tree. Based on that conditions only, based on that properties of B-Tree only, whether we can perform the insertion or deletion also, right? And based on that, you can see leaf node contain more than minimum number of keys. If more number of keys are there, then we can able to delete the leaf node directly. The other case, the leaf node contains minimum number of keys. Suppose it should maintain only 2 keys, right? In this case, if I am trying to delete, it has to maintain. That means the leaf node has to maintain minimum number of 2 keys. But in that particular case, if I am going to delete a particular element from that leaf node, then it is not satisfying the property of our B-tree. So, to avoid that situation, we are going to follow some other cases. What are the cases here we are going to look? Look here, these are the 3 cases, that one we are going to follow. What are the 3 cases? Borrow from the immediate left sibling. If I don't have the minimum elements, then I am going to borrow it from the immediate left sibling. From the siblings, I am going to borrow, right? In the left sibling also, if I don't have the minimum number of elements, then I can borrow it from the immediate right sibling. In both the cases, these 2 are not possible. In that case, we are going to merge the elements from the root node, and so that we are going to merge it. First, we are going to merge it, and based on that, the element is going to be deleted and the remaining elements are going to be placed in the appropriate positions. Okay. Like this way, these are the cases where we are going to look into the B-Tree-Deletion. And the other case, the first case is the target key is a leaf node. If it is a leaf node, we are going to check for all the cases. Next, if the target key is an internal node. Internal node means in between. That means other than the root node, whatever the nodes we are going to have in the tree, those are nothing but the internal nodes. Here you can see 23 and 90 are the internal nodes, right? Now, if it is an internal node, if I want to delete an internal node, in that case, how we are going to delete? We are going to check with the in-order predecessor. We are going to replace with the in-order predecessor, and we are going to delete the element. And otherwise, we can select an in-order successor and we can delete it. And if you don't have the minimum elements, then in that particular case, we are going to merge it, and based on the merging, we are going to delete the particular element and the remaining elements will be placed in the appropriate position. Okay. Now consider here, this is the example where we have constructed a B-tree of order 4. Here m equal to 4. From this m equal to 4, how many maximum number of keys I can store? Maximum number of keys equal to m minus 1, that is nothing but 4 minus 1, that is 3. Here I can store 3 keys. And how many minimum number of keys I need to maintain? That is floor of seal of m by 2 minus 1. What is the seal value? This is nothing but 4 by 2 minus 1. 4 by 2 value is nothing but 2. 2 minus 1, we are going to have 1. At least one minimum key value should be present in the tree, right? We can't delete all the nodes from the B-tree of order 4. At least one key has to be present, right? According to this tree has been constructed. Now, we will be looking into all the cases what we have seen in the case 1. Now, case 1. Observe, the target is a leaf node. First case we have seen, right? We have again some classifications there. This is a tree. This is a B-tree. I want to delete a leaf node. What is the leaf node I want to delete? I want to delete 98. What is the condition we have? If the leaf node is having more than minimum number of keys. Just observe this node. This node is having maximum number of minimum number of keys. That means it can maintain only one key, but it has 3 keys. No problem. I can directly delete this 98. You can delete that 98 directly, and after deleting it, you can check how many number of keys it is having. It is having 2 keys, that is 93 and 96. That is, it is maintaining minimum number of keys. That's why you don't have any problem. Directly we can delete this 98. After deleting 98, we are going to get the tree like this. Directly we are going to remove 98. We are going to have the tree in this format. Now, the other case. Now I want to delete 60. I want to delete 60. 60 is a leaf node or not? Once you check, yes, 60 is a leaf node. You can search the element is present in the B tree or not as of our BST property, right? 60 is present, right? Now, if I want to delete 60, is this satisfying the property of B tree? No. Why? Because it has to maintain minimum 1 key. But if I am going to delete 60, it is becoming 0. That's why we are unable to delete directly. Now, what we need to do? We are going to check the other cases. We can either borrow it from the left sibling or right sibling. But here we don't have the left sibling for this tree, right? We have the right sibling, right? Because of that, we are going to borrow it from the right sibling. When I am going to borrow it from the right sibling, can I directly borrow it to here? No. Why? Because if I am going to borrow 93 here, I am deleting 60. What happens? When I am going to place 93 here, observe, it is not satisfying our BST property. That's why what we need to do, first we need to move this 93 to the top, then moving 90 to down so that we can delete 60. That means what we need to do, 93 has to move here and 90 has to move here, and so that we can remove the element 60. Now, if I am removing 93 from here, I am getting only 96. That means I have only one minimum element in the B tree. It is satisfying our property of B tree, right? Now, after updating the tree, this is your tree. Now, the tree is also balanced. Now, you can check 93 is as the root node and 90 is the left child and 96 is the right child. It is satisfying our BST also. The next one. Now I want to delete 90. I want to delete 90. Now, when you can see 90, how we are going to check whether 90 is there or not? First, it will be checking with 32. 90 is greater than 32. Move to the right. 90 is less than 93. Move to the left of it. Like this way, we are going to search the element in the B tree. After reaching to that 90, now I want to delete this 90. What is the first case I need to check? If I am going to delete it, it is not going to have the minimum number of keys that is going to be present. So that what we need to do, we need to borrow it from the left sibling. I don't have the left sibling, so that I am unable to borrow it. From right sibling, if I am going to borrow, then it is also becomes 0. Right? It should also maintain minimum number of keys. It is also not possible. Right? You don't have the left sibling and right sibling are having more number of keys, so that we are unable to borrow it from them. So, now what we need to do? We need to merge them. How we are going to merge it? Directly we can't merge 90 and 96. We are going to merge with the parent also. That means 90, 93 and 96. These three are going to be merged. Right? After merging all these three, right? All these three are going to be merged. Now I can able to delete the element 90. 90 will be deleted. Now after deleting 90, now we are having two elements, 93 and 96 are present. 93 and 96 are present. Now what we need to do? We need to place this 93 and 96 as left and that is which is the parent node and which is the child node. Now we are going to make 96 as the parent node, right? We are going to make 96 as the parent node and 93 becomes the child node of it, right? We merge both the nodes. When you are merging these nodes means directly we can't merge, so we need to consider these two, parent also. 90, 93 and 96 are going to be merged. So, when I am going to merge it, I am going to delete 90. So, 93 will come as a left child and 96 becomes the parent. node, right? Now you can see the same diagrammatic representation, how that will be changed here, right? After deleting 90, this is the tree where we are going to get it. Okay. Now, what is the other case? If my target node is an internal node, we have seen up to now the leaf node deletion. Now we are going to delete the internal nodes. Now, I am going to delete the internal node 23. 23 is the internal node and 96 is also the internal node. If I am going to delete 23, now what are the conditions we have? Either we can have the in-order predecessor or in-order successor, or we can, if you don't have in-order predecessor and successor, we can perform the merging also. 3 cases are there. Now, I am going to check with the in-order predecessor. But here we have only 2 elements. But I am going to check with the right side of the tree. I have 3 elements, so I can borrow the element from the in-order successor. Either we can take it from the in-order predecessor or successor. Both of the things we can take. But I am going with the in-order successor. I am going to borrow an element from the in-order successor. Now, which of the element has to move up? If I want to delete 23 means 29 is going to move up and the remaining leftover elements of 30 and 31. After removing or moving, now you can check is it satisfying the property of that B-tree. Yes, it is. It can maintain minimum of 1 element, so that I have 2 elements, no problem, right? Directly I can do this deletion. As you can see, I have moved 29 here. Now I have 30 and 31 here. Now I want to delete 29. 29 element I want to delete, right? In that particular case, what happens? I can either borrow it from the left or right subtree. That is nothing but either we can take the in-order predecessor or in-order successor. Any one of them can be taken, right? If I want to delete 29, I can replace this with either 15 or either 30, any of them. Any one can be replaced, not both, right? Like that way we can perform the deletion. And when you are going to see the advantages of B-trees, this will be well suited for big data sets. Big data sets, if I am going to consider, for that big data sets, we can use these B-trees. And the real-time applications, because they have a guaranteed time complexity also. In the real-time applications, we don't have the small data sets. We will be having the larger data sets. In that particular case, this will be more applicable when we are going to check with the time complexity and to perform any fundamental operations like insertion, deletion, searching, right? And with B-trees, we have balance. B-trees can balance themselves. This is one advantage. And high throughput and concurrency, right? This terminology you come across this OS operating system subject. Efficient usage of storage space also, right? There will not be wastage of space. More space can be used here. This is the advantage here. And what are the disadvantages you find with the B-trees? They are dependent on the disk-based data structures, right? And can use a lot of disk space. Here mainly it will be working on the disk spaces. How you are going to store your data, right? Not always the greatest option, this B-trees, and comparatively slower to the other data structures like arrays and linked lists. This will be a little bit slower. And let us see the summary of this session. In this, we have discussed about what is searching, that is how you are going to perform B-tree search, and how you are going to perform deletion, B-tree deletion also. While performing B-tree deletion, we have to check for 2 cases. One is if the target value is the leaf node, what are the conditions we need to follow? And if the target value is the internal node, what are conditions we need to follow, right? I hope you understand this concept. Thank you.